Hi everyone, thank you for coming to my talk. I really appreciate it. Today I'll be talking about I/O rings on Windows, a concept that is really new to the Windows world and will hopefully help you improve your application's portability and maybe even performance. So before we start, a few words about me. My name is Yarden Shafir. I currently work as a software engineer at CrowdStrike. Previously, I worked for SentinelOne. I work on our EDR program, developing detection features. I also teach Windows internals classes together at Alice UNESCO and Winsider. I give conference talks. I write blog posts and tools, etc. And other than that, I'm also a circus artist. In COVID times, mostly an unemployed circus artist. I do aerial acrobatics. I teach circus and aerial. And before that, I used to be a pastry chef for a while. So feel free to ask me questions about pretty much any topic you would like. Now onto the topic. I/O rings are something that is new on Windows, but isn't so new in the computer world in general. It's existed on Linux for a few years now under the name I/O ring, and basically it's a way to asynchronously queue I/O operations. Instead of reading one file and waiting for it to complete, and then writing to one file and waiting for it to complete, and then reading another file and waiting on that, you can queue a whole lot of different I/O operations to happen whenever they happen. And while they are happening, your application can keep running or wait on something and just go check on the events later when they're done. And because they're implemented in a ring concept, you also don't need to worry about overflows. You can queue a whole lot of different things at the same time, and it works pretty efficiently. And after it's been implemented on Linux for a few years, now Windows is implementing it, which is very cool. It's a really big change for Windows that could help the portability of applications. You won't need to create a completely different I/O mechanism to support different operating systems. And because it's completely asynchronous, it could also have some performance benefits. Now, on Windows, this whole mechanism is implemented in the kernel, where all other I/O is implemented. It has system calls to communicate with it in NTDLL, and there are wrapper functions, which are going to be the documented functions implemented in KernelBase.dll. They are currently not officially documented yet because this is still a work in progress, but there is already a header file in the preview builds called I/O ring API. So you can look at that and learn what is currently implemented, even though it's still work in progress. So basically, to use an I/O ring, what you need to do is first create one. You need to tell the system, hey, I am creating a new I/O ring. It creates in Windows a new object type, has pointers to it, has references to it, and you get back a handle. That handle will communicate with the object, but you also get a structure with all the information you need to operate the I/O ring, which has a few different things in it, but the two main things are the pointers and sizes of the submission queue and completion queue. Because you have a submission queue where you will put the information of all the different I/O operations that you want to perform. You will submit them to the kernel through a submit API. And then once all the operations are completed, the kernel will write the results of all the operations into a different queue called a completion queue, where your application can go and read that. And when you read a completion queue, you also need to tell the system what is the latest completion event you read, so the system won't write over it, but we'll get to that later. So basically, there are 4 basic steps. You need to create an IO ring, you need to write the data into the submission queue that you received, then you need to submit all your operations, and then once all operations are done, you can go and read all the results from the completion queue. This is implemented on Windows very similarly to the way it does on Linux. Linux has those same steps. They're implemented very similarly with very minor differences that are mostly about the way memory is handled in those operating systems. So if you know how IOU ring works on Linux, it's pretty much the same. So now on Windows, when you create a new IO ring object, it creates a new object of type IO ring in the system. It's an undocumented structure that I documented a few months ago in a blog post. And that contains all the different structures, all the different data the system needs to manage this IO ring. What the system also does, which it doesn't do on Linux, is that it allocates the submission and completion queue and maps them to user mode. So by the time the creation API returns, your application doesn't need to do anything to finish setting up the IO ring. Everything is already set up. Both queues are allocated based on the size that you requested, and they're mapped to user mode, so you can just start using them without doing anything else. Now, the limits for the sizes are you can have up to 10,000 hex entries in the submission queue and up to 20,000 hex entries in the completion queue. That doesn't mean those are all the IO events you can have in the system. It just means that's the maximum number of events one IO ring can support. If you need to do more than that, you can create multiple IO rings. You can even use them in separate threads. So you can even multitask the creation and setting up of and submission of the IO rings. But this is as much as one IO ring is going to support. Now for operations. Like I said, IO rings on Windows are still a work in progress. This is also why the header is still only exists in preview builds, and none of this is documented. Because right now, the only IO operation that IO rings on Windows supports is read. For example, you can't do any writing using IO rings yet. So right now, IO rings support 4 operations. They support reading a file, they support registering files and buffers, and they support canceling an operation. Now, the first and last one are pretty clear. The second and third are specific to IO rings, because unlike on Linux, on Windows, when you register an operation in an IO ring, you can register it with a file handle to read and a buffer to read to, but you can also pre-register files or pre-register buffers. You can use IO ring OP register files to register an array of up to 10,000 hex file handles that the IO ring now has a pointer to and knows how to access. And you can pre-register an array of buffers just the same way. And this way, when you register a read operation, you don't necessarily need to give it a file handle and a buffer. You can also give it an index to a file handle or an index to a buffer. And then the system will read the handle or buffer in that index in the array that you pre-registered. It works very similarly. You can specify whether you're passing in a handle or buffer or an index through specific flags when you set up the queue entry, but you can do both. And of course, you can also cancel an operation. Now, when you submit an IO ring for processing, you don't necessarily need to fill in all the IO ring entries. You can set up a ring that supports up to 1,000 entries and only submit 1 or 2 or 5. You can also write more entries that you're going to submit. You can set up 20 entries and only submit the first 2 for processing if you want to do that for whatever reason. When you submit an IO ring, you tell the system what ring you're submitting through the handle. You tell it how many entries you're going to submit, and you get back the number of entries that were processed successfully. When you submit the IO ring, the system is going to read the submission queues, the submission queue that's made up of submission queue entries, SQEs. Each submission queue entry has an opcode, meaning are you going to read, pre-register files, buffers, or cancel an operation, and it has all the information that's needed. Now, before all the SQAs, there is a header that tells the system how many entries have already been processed, how many entries still need to be processed, and what is the last processed entry. Because this is a ring, there isn't exactly an index because it goes in a circle. So it just tells the system what is the current head and tail of the ring, so it knows where to start and how many entries to process. So for the more visual learners here, this is pretty much what it looks like. Every SQE, submission queue entry, if the diagram was bigger, then we would see that the SQE is actually part of the whole submission queue, and after the SQE there is another one, another one, and another one. But if we look at one SQE, it has an operation and flags, and then it has either a file ref or offset. I didn't show it too well here, but this is actually a union. So there is either a file handle or a file offset in the array, and then another union, either a buffer or, sorry, these are not a union. The file ref can either be a file handle or an index. Then there's an offset to read inside the file. And then the buffer, which is again a union, which can be either either a pointer to a buffer or an index, then a buffer offset and size to write into the data that was read from the file. Now, I won't talk about the system calls, which are the undocumented way to use that, because you technically shouldn't be using system calls directly. You should be using the wrappers. So the wrappers are implemented in KernelBase, which you can already use, even though MSDN hasn't documented that yet. So what you would do here is, this is simplified code. You will create an IO ring using create IO ring. Then you will build all the different SQEs using build IO ring functions. Here I just wanted to read one file for this example, so I'm calling build IO ring read file. There are also other build IO ring functions for different operations, and you can call that with as many files as you want, as long as your ring supports that many. Then you submit through submit IO ring, and then you call pop IO ring completion to read the completion status. Of course, if you call pop IO ring completion before the operation was actually completed, then you will get the previous completion event, not the current one. So you will need to wait. This is not part of the code here because there is only so much room on the slide, but there is a set IO ring completion event function that allows you to create a new event and set it as a completion event for this IO ring, meaning this event will be signaled when all the operations are completed. So if you want, you can have a thread that just waits on the completion event, gets signaled, basically gets woken up when the completion event gets signaled, meaning all the operations are completed. And then you can start calling pop IO ring completion to see the results. Now for the most interesting part for most of you, how does this actually affect my application? Because one of the benefits of IO rings is performance improvements. That's why we're doing asynchronous IO operations. So I'm not a performance expert, so the numbers here are pretty rough, and we need more performance analysis done on different systems, on different CPUs to get more accurate numbers. But basically, I wrote a pretty simple code that read around 4,000 files and then sort of fake hashed them. And by fake hash, I mean I just made a sum of the values of all the bytes of all the read data just to process the files in some way. So I did that in four different ways, using the legacy read file, which is synchronous, read file EX, which uses completion ports, and then in two different ways using IO rings. First with the official Win32 API, similar to what you see here, and then with the internal undocumented NT API, the direct system calls. So the numbers here are clock ticks, which are not the nicest way to view time, but it's the most accurate. So I will save you the trouble of figuring out the exact values and differences here. Basically, we can see that in general, IO rings are faster. Obviously, the slowest one is the synchronous read file. The read file EX is about 2% faster than read file. I ran the application around 30 to 50 times to get a decent average. So read file EX is about 2% faster than read file. And then using IO rings is in general around 2% faster than read file EX. The results are pretty inconclusive because there's a lot of variance related to caching and things like that. But I got a pretty consistent 2% improvements in IO rings over asynchronous read using IO ports. In some cases, the improvement was even up to 5%, but those were relative edge cases. When talking about IO and performance, 2% improvement, which turns into 4 or 5% improvement over synchronous operations, can be a pretty huge deal. So IO rings are not completed yet. They can still change. They're not documented yet. But it could be a pretty major change for Windows. Now we're getting pretty close to the end of the talk, so I will summarize all of this. This was a pretty shallow review of IO rings. Obviously, there is a whole lot more to know about them and to learn about them. And part of that is that we will need to get more information once the feature is actually complete, because Windows is not going to just support reads forever. In future builds, they will support other operations. The first will probably be file write and flush, because those are the most common ones. So I'd expect to see them pretty soon. And the internal implementation can still change, because again, this is not yet complete. Once the feature is complete, we'll probably see official MSDN documentation and examples and new ways to use that. But first, as we saw, there is a performance benefit here that is pretty major. It's the same as the performance improvement between synchronous and asynchronous reads. The second thing is portability, because Linux doesn't support, for example, asynchronous operations using completion ports, but Linux does support IOU rings. So when both operating systems support IO rings, you would need pretty minor changes to port your application from one operating system to the other. You won't have to completely rewrite it. So that's another major improvement. That doesn't necessarily impact the application performance, but that definitely impacts the performance of the team and the company. So I'm really glad you joined me for this talk. I hope you enjoyed it. I hope you learned more than you did before. If you want to know more, then I published a blog post covering IO rings on Windows a few months ago. I will probably publish some more information pretty soon. And here are my contact details. Feel free to contact me through email or through my Twitter handle. I try to be responsive on both. So if you have any further questions on that, I will be happy to answer or direct you to resources. And again, thank you for coming to this talk. Hope you all have a great day.